You can start.
Thank you, Irina. Thank you. I would like to thank you all for the presence in this lecture, and in special for my supervisors, John, Pavel Zalesky, and Thomas Weigel. And this is entitled Infinite Graphs of Groups, and it's a joint work with Pavel Zalesky. So I will make a brief introduction and some basic aspects of the theory. Next, I will present this part one, the profinite completion of the fundamental group of infinite graphs of groups, that I will explain what all of this means. And in the last part, I will applicate these to virtually free groups. So the Serre theory of groups acting on trees appeared in 1968 to 1971 and changed completely the face of combinatorial group theory. It appeared in the Serre book Trees, and it gave understanding that the main constructions of classical combinatorial group theory can be expressed uniformly as group acting on trees that allow it to use the metric of the tree instead of manipulation with words of the elements of a group. So in the 80s, the need of such theory appeared in the category of profinite groups. And it's more important, I can say, because an element of a profinite group cannot be written as a word of generators. So the profinite version of the Serre theory is very useful, and many results of modern profinite group theory is based on it. So this profinite version was initiated in a paper by Gilden Ruiz and Ribes, and then developed in a series of papers by Melnikov, Ribes, and Pavel Zalesky. In 2017, Ribes published a book on the subject, compiling the main results of the theory. And since the profinite version does not arise with full strength, interrelation between the abstract and profinite words provide an useful tool to unravel interesting applications. So I will try to show some of these applications that I have developed with Professor Pavel Zalesky. So this presentation is divided in two parts. In the first one, we present a new definition for the fundamental group of a graph of profinite groups using the language of paths. That is more natural than the previous definition that Ribes presents on his book. And given an infinite graph of groups, we construct a profinite graph of groups which answers the open question 6.7.1 of the book of Ribes. That is profinite graphs and groups. In the second part, we apply the results presented in part one to virtually free groups, solving two problems. The first one generalizes the main result of a paper by Ribes and Zalesky, and published in the Iberoamericana journal, and answers open question 15.11.10 by showing that if G is a virtually free group, the normalizer of finitely generated subgroup H of G is dense in this normalizer on G hat. The second generalizes the main result of a paper by Chagas and Zalesski and answers open question 15.11.11 of the book of Ribes, the same book, by showing that every virtually free group is subgroup conjugacy separable. So part one is the name of the paper, the profinite completion of the fundamental group of infinite graphs of groups. So first, what is a graph of groups? We start with connected graph, a gamma, abstract connected graph, and two instance maps, D0 and D1 from gamma 2. So a graph of groups is a sheaf of groups together with gamma and together with two morphism of sheaves. And this is where this is defined to be the restriction sheaf, and the restriction of each of these DIs to GV is the identity map on the sheaf of vertices. And in addition, we assume that the restriction of delta del I to each fiber, GM, is an injection. So to understand this more properly with an example, we can start with this connected graph gamma. And now we associate to each vertex and each edge a group such that the edge groups are embedded into the vertex groups. So to this vertex V1, we associated the dihedral 4. To this edge, we associated the cyclic 2 group. And to these, we associated the dihedral 8. And we note that, for example, D4 is actually D8 quotiented by the center. And in each of these, we can embed the edge groups into the vertex groups. So now we can extend this to the profinite universe. So we start with a definition of a profinite space that it's the inverse limit of finite discrete spaces. And a profinite graph is a profinite space with a graph structure where the vertex set is closed. So it can also be written as the inverse limit of finite graphs, and it's said to be connected if the images of the finite projections of gamma are connected as abstract graphs. So to understand this, we present an example. So let N be the set of natural numbers with the induced subspace topology from R, and N bar be another copy of N. So now this union N with N bar is Hausdorff and locally compact. So we can define gamma as the one-point compactification of this space. So since it's Hausdorff, totally disconnected, and compact, it's a profinite space. And now we can define a graph structure that is gamma equals N union the one point infinity. The edges of gamma is N. We note that the vertex set is closed here. And for instance maps, we define these two maps. And a representation of this graph is the following. So we can represent this. And now we can define a profinite graph of groups. So it's basically the same definition, but now gamma is a profinite graph, and we have to pay attention to the continuity of the instance maps, and that the vertex set now is closed. So we have the same definition, and now the pre-images of the fibers are profinite groups or pro-C groups if you are working with any other variety of finite groups. So an example, if we have the same profinite graph, we just define it. Now we can associate to each vertex and each edge a profinite group such that the edge groups are embedded into the vertex groups. So this is one form of doing this. Here, the dihedral groups, and we can endow it with the discrete topology. And here we have the profinite completion of the dihedral infinity, and here cyclic groups. So related to this graph of groups, we can, there is an associated group called the fundamental group of the graph of groups. So in the book of Ribes, the profinite graph of groups is it's a profinite group such that it respects this universal property. So these maps are defined based on sections and zero sections and a lot of technical things, but the idea here is that we have a map from the graph of groups to this group. It's a morphism of shifts related to this group. And here it's the fundamental group of the profinite graph. It's also defined, and we can define a map V prime that is from the fundamental group to the fundamental group of the graph of groups. And for any profinite group H, this map delta induced is unique. And these nu and ni prime are related in some sense, but I will not explain it further. So the idea is that the profinite group is defined as universal property. And it's complicated to work with this when we are dealing with inverse limits. That is very usual in the profinite world. So by construction, it's actually the co-product of the vertex groups and now co-product with the fundamental group of the graph, quotiented by the topological closure of the normal subgroup of this group generated by this set. That it's related to the relations between the ni and ni prime functions. So we establish a new definition, and it's based in the following. Let C be a path on the abstract graph gamma with length n equals L of C, such that Vj is a vertex, Ej is an edge, and this J varies from 0 to n. So a word of type C in this group F G gamma, this F is the free product of the vertices groups, free product with the fundamental group of the free group with base the edges set quotiented by some n, is a pair C mi, where this mi is a sequence of elements, each one in vertex groups. So this element is an element of vertex group and edge, an element of vertex group and edge, and following like this. So the abstract fundamental group is with a base point V is defined to be this element C mi, where the initial and the final vertex of the path C is the same vertex. So they are loops such that the elements are element of the vertex group, edge, element of vertex group, and edge, and it follows this way. So there is this proposition from Bass, 1993, that he says that a morphism of graph of groups, so it's a morphism of shifts. We have these from alpha maps groups to groups, and alpha prime maps the graphs to graphs. So this induces a morphism of fundamental groups, beta from the profinite, from the fundamental group with a base point V to the fundamental group with base point V prime, defined by this, this map. So Bass does not define this map properly with this notation, but we changed it a little to allow us to define the fundamental group with a base point V. So now it's defined, we take the map on the graph, we take the same path, the image of it by alpha prime, and now from alpha of me, it's a map of groups, and we take the image of these elements in the vertex groups. So now this proposition with Ribes-Zalesski, I have that the inverse limit of finite abstract graphs of finite groups induces an inverse limit of profinite completions of abstract groups. And now we define this as the fundamental group with a base point V, and the profinite fundamental group with a base point V, and it's denoted this way. So with this new definition, we have equivalence between these two definitions. And now we can work with these to prove interesting results. So let G gamma be a finite graph of groups. We can construct a profinite graph of groups such that this is the profinite completion of GM because gamma is automatically profinite. Moreover, the fundamental group is the profinite completion of the abstract fundamental group, and the abstract standard tree is densely embedded in the profinite standard tree. So the standard tree is just the graph of groups such that the fundamental group acts and it generates the graph itself. So it arises a question that's open question 6.7.1 in Ribes. Is it possible to do a similar construction in the case when gamma is infinite? So the answer is yes, and it's this theorem with Zalesski that if G gamma is an abstract reduced graph with finite groups of an abstract graph gamma, such that the fundamental group is residually C, and there exists a profinite graph that contains gamma as a dense subgraph, and a profinite graph of finite groups with G bar being equals to GM, such that the profinite group is the profinite completion, and the standard tree is densely embedded in the standard profinite tree, in such a way that the action extends the natural action in the abstract case. So actually, we can generalize this to the Pro-C case and to the case with the groups are not necessarily finite. So in this case, there is still exists a graph of groups such that gamma is densely embedded in gamma bar. For each M, its vertex groups is the profinite completion of M. The fundamental Pro-C group is the Pro-C completion of G, and this graph is injective. And the graph of groups decomposes as a surjective inverse limit of finite graphs of finite C groups, and the fundamental group is actually the inverse limit of the profinite completions of the abstract finite groups. So idea of the proof, we take U be a collection of open normal subgroups. In the Pro-C topology, we define GUM this way, and now we define an equivalence relation. And so gamma U, gamma by this equivalence relation is finite, and now we can define a finite graph of finite groups, putting GUM bar equals GUM, and now we have maps from this del I from GU bar, and we can induce an inverse system. So since we have maps of graphs of groups by best proposition, we have induced maps from fundamental groups with based points. And now we take inverse system of graphs of groups, and we put this G bar, gamma bar as the inverse limit of GU gamma U. And now the profinite the pro-C fundamental group of these equals the inverse limit of the finite cases and the profinite completion of each of them. So we can generalize these also for the standard tree, and we assume the same hypothesis, and we ask in addition that GM is closed in the pro-C topology of G for every M. Then the standard tree is densely embedded in the standard C tree, and the action extends the natural action on the abstract case. So part 2 is application to virtually free groups. We start this part with a theorem by Scott that every virtually free group G is the abstract fundamental group of a graph of finite groups. So we can combine the last two theorems of part 1 with Scott's theorem. So if G is virtually free, then it's the abstract fundamental group pi1 of G gamma of a graph of groups, such that Gm is a finite group. So now we can construct by the theorems of part 1 a profinite fundamental group and a profinite graph of groups, such that the profinite fundamental group is G hat, and it decomposes as a surjective inverse limit of finite graphs of groups. Now we have this pi u from the fundamental group to the completions with the natural projection, and define GU as this pi u of GU gamma u and HU as the closure of pi u h. By the finitely generated version of this theorem that appears on the paper of Zalesski and Ribes, we have that this closure equals the normalizer in the profinite completion. Applying the inverse limit, we have the following result, that it's a theorem with Ribes-Zalesski that let G be a virtually free group and H a finitely generated subgroup of G. Then the closure of the normalizer equals the normalizer of the closure in the profinite completion. So this theorem generalizes the main result of the paper by Ribes and Zalesski and answers the open question 15.11.10 of the book of Ribes. And we prove in the paper a more general case, namely the pro-C. And the last application is for subgroup conjugacy separability. A group G is said to be subgroup conjugacy separable if whenever H1 and H2 are finitely generated closed subgroups of G in its profinite topology, then H1 and H2 are conjugated in G if and only if their images in every finite quotient G over N are conjugate. So again, using the last theorems of part 1 and the theorem by Scott, we have proved the following result. So let G be a virtually free group, then G is conjugacy, subgroup conjugacy separable. So this theorem answers open question 15.11.11 of the same book of Ribes and generalizes the main result of Chagas and Zalesski, where it's proved for the finitely generated 3 by finite groups. In the paper, we proved the pro-C version. So here is the bibliography I have used. This is our paper that is submitted for publication. And this is the paper of Bas from where I took the proposition. This is the paper by Chagas and Zalesski, subgroup conjugacy separability of 3 by finite groups, that we generalized the main result. And we also generalized the main result of this paper, normalizers in groups in the profinite completions, published in Revista de Matemática Ibero-Americana. And the book Ribes published in 2017 is these profinite graphs and groups. And this book by Serre, Trees, presents the abstract version of the Basset theory. So I think that's all. Thank you for your attention.
Thank you, Mattheus. Some comments, questions? Welcome, please.